Okay, so we have an inclined plane with a pulley. Woohoo! Alright, so the first thing we want to do is to label all the forces that we have. We have two boxes, two masses. Mass 1 is 7 kilograms, mass 2 is 5 kilograms. We're looking for our net force, which is going to cause the object to move one way or the other. It's going to accelerate in the direction of that net force. We're looking for the tension. We have one rope, we have one tension, and we're looking for the acceleration. So I always go for my weight first, or my force of gravity first. So that's that value. And I'm going to say this one is about like that. I'm going to label this one as M2G. Right, because it's mass 2 times just the acceleration due to gravity, because there is nothing to break down into components. It's directly vertical. With this one, this is also, this is M1G, but you'll see that this surface is at an angle to the weight, which means I'm going to have to break the weight into components. Like that. This is going to be considered my F perpendicular. I've got my normal. I know these are equal because it's not, the mass isn't sinking into the inclined plane. The mass isn't levitating off the inclined plane. So I know that these two forces are balanced. This is going to be considered my F parallel. This direction. This is going to be moving down. So this is really my F parallel up here, if you look at it like that. So I've broken my weight down into this component and this component. So this is going to be let me pause this for just a second. Okay, so this parallel force is really going to be, this is opposite side, right? So let's label this as opposite this angle. Remember that this angle is the same as this angle, and I've shown you that before. This is 21 degrees. It's opposite. This is adjacent to the angle, and this would then be hypotenuse. Okay, so always on the inclined plane, your hypotenuse is the weight. Okay, F parallel, F perpendicular. So if this is the opposite angle, this is my weight force, which is the hypotenuse, and I can calculate that, right? 7 times 10, remember we're going to use G as 10. So 7 times 10 is 70. So I know this number, I'm looking for this number, and I have the angle. So I'm not going to use my perpendicular force here. It doesn't really matter because it's going to balance out anyway with the normal force, so I don't need to calculate it. I can use this value plus the angle to calculate that using SOHCAHTOA. OH is SO. So I'm using SO of SOHCAHTOA. So this is really this hypotenuse, which is, we'll label it as M1G, and that's going to be sine theta. That's how I'm going to get that number. All right. Now, when I'm looking at this system and I'm trying to decide how it's going to move, I am going to define that. So let's just say that I think it's going to move this direction, and I'm going to consider that direction positive, up and over positive. Now you know from our discussion in class that if your F parallel is greater than this weight, it will go this direction. You also know that if this F parallel is equal to this weight, that is not going to move, even on a friction-free surface. We also know that if this F parallel is less than this weight, okay, less than this weight, it will actually come down this way, up and over. So I'm going to define, I'm not going to do that calculation yet, but I'm just going to go ahead and define my system this direction. And I'm going to say that is positive. When I'm looking at the forces, when I'm doing, and I do this because I'm going to have to total all the forces acting on the system. And that means forces, because they are vector quantities, have magnitude and direction. The directional component will tell us positive or negative. So we just have to define what that directional component is. We can't really be wrong, right? If we get a different, we're going to get the same magnitude regardless. We're just going to get the positive or the negative, for example, with the acceleration. If we define this way as positive and we get a negative acceleration, just means, oops, actually went this way. No big deal, okay? When we're looking at which forces actually go, like which forces do we look at? Do we look at the F normal? Do we look at the perpendicular? Do we look at this weight? Do we look at this weight again? Do we look at the F parallel? So many choices. So what you're looking at really is, and I'm going to highlight this for you, you're really looking at what's in line with this green highlighter. You're looking at really what's in line with that because you're following the line of this motion. Now, something that we didn't put in yet is, and hopefully you've seen this, or you recognize that I didn't put it in yet, is that we have tension in this rope. Now it's one rope, so we just have one tension. The mass is pulling the object this way, the mass is pulling the object this way. So the tension in the rope is going against that, right? Newton's third law, going against that from this side and this side. So we would draw the tension up from those masses. I'm going to just label them as T. All right, so now we just have to do our F net. So we're going to calculate F net with F net equals MA. So that's just going to be part of that calculation. So we have F net equals the mass of the system times the acceleration of the system. So we're going to say, all right, here's our F parallel. This arrow is going down. I've defined up as positive, so this is negative. So I'm going to say negative M1G sine theta, because that's really what F parallel is. Again, this is not in my line, so I'm going to go to this guy. So this is tension. It's going in the same direction as what I've defined. I go around my pulley system. This is the other tension. It's the same tension, but we're looking at it. It's going up, positive is down, so it's minus T. And then my last thing here is my weight. So we've got our vector going down here. This down is positive, so we're going to say plus M2G. Important to keep in mind which mass you're talking about. So that's why we labeled it M1 and M2. So a quick calculation will show, and this is equals MA per second. Let's look at M1, M2 is really 12. We're looking at the total of the system times A, right? The system will move together because it's an attached mass and mass. So plus T minus T, we can get rid of that. If I do the first mass times acceleration due to gravity, which is the weight of the object, so that's really 70 times sine 21, then I'm actually going to get negative 25.09. That's newtons. Now I would carry as many numbers as possible. I'm just rounding off for right now, just to make it easier for me. I've got the weight of this object, which is really going to be 5 times 10, which is 50, equals 12 kilograms times A. So if I add these two together, I'm going to get negative 24.91, or positive actually. Newtons equals 12 kilograms times A, divide this out, divide this out. Now remember that, so we just found the F net. This is the F net, so let's go ahead and put this number here. This is positive 24.91 newtons. Remember that a newton is really kilogram times meter per second squared. So don't write your answer as newton over kilogram. It's going to be in meters per second squared. Right? Newton equals this. That's why the kilogram will cancel. This is going to be, and I need to get my other calculator, so hold on just a second. It's going to be 2 point something. Okay, so my calculator says this is a positive 2.08 meters per second squared. So I can put that value here, positive 2.08 meters per second squared. Now what does that tell me? That tells me that I actually picked the right direction, that it's going to fall here. And the reason it's going to do that is because if you go back to the problem, do you see how 25.09 compared to the weight of the other object, this is less than the weight over here. So you're really comparing these two forces to know which direction it's actually going to move. So it's going to go up and over. 2.08 meters per second each second is going to be how it's going to accelerate. Now we're going to look at tension. And for tension, we really just need to focus on one of the boxes, since the tension here should be equal to the tension here. So it really doesn't matter which box you use. I'm going to go with this one because I only have two forces to deal with instead of this one, this one, this one, this one, although these are going to cancel out. I don't have to do sine anymore if I choose this one, so I'm just going to choose this one for my T, or to find tension. So again, in order to find T, I'm going to say F net equals mass times acceleration. I'm going to go back, use the same defined direction. So I have the positive m2g, right, minus T equals the mass, which is 5, because we're only looking at that, times the acceleration of the system, because this mass is going to accelerate with the system. So that's going to be close to, this should be 10.4, but let me just double check. Haven't had coffee yet. So 10.4 newtons equals negative 10. And we already found the weight of this object is 50. So that's positive 50 newtons, right? 5 times 10. 5 times 10. That's how I got this number. Okay. Minus 50, minus 50. So I have negative T equals negative 39.6 newtons. But remember, tension is never negative, so it's going to be positive 39.6 newtons. The reason tension is never negative is that tension can't actually pull something down. It's actually holding it up. It's going against the pull down. So a rope or string or wire can't actually push something. Okay, it can actually just pull it. So we're going to put this as a positive 39.6 newtons. So we have figured out what our F net is, what our tension is, and what our acceleration is, and that's a pretty good sample problem of how to do a 2-mass pulley on an inclined plane, frictionless.